Let's start chapter 6.2, which is called Integration by Parts, which we'll abbreviate as IBP a lot. Why should we care about integration by parts? Well, here's two problems where we aren't yet able to integrate the functions. If you keep track of something like blood sugar, as time goes on, if the person has a meal, their blood sugar goes up and then comes back down again, maybe a little slower than going down than coming up. What kind of function might model that? Well, that kind of looks like a surge curve, like t squared e to the minus t, but then shifted up 100, because that usually just goes through 0, 0. So the 100 plus is easy to integrate, but this t squared e to the negative t, we don't know how to integrate yet. What about for something mechanical that's oscillating, like if you're driving along and hit a speed bump and your car goes boing, hopefully it should only do that once, my mechanic tells me, but if your shocks are bad, or if you're a mechanical engineer designing the system, maybe sometimes the system does this, sometimes it does the right thing, depending on what kind of spring constant or fluid you put in the shocks. What kind of formula might describe this function? Think about that for a sec. Well, I see some sine wave kind of oscillation, but with a dying down amplitude. So you might say sine omega t. Omega is a frequency that you can adjust to make it oscillate faster or slower. And then amplitude out front that is decaying. It could be e to the negative 3t or excuse me, whatever. So we don't know how to take the integral or the antiderivative of either of those yet. You might think u substitution. U substitution doesn't work. So that's what we're going to learn how to do with integration by parts. So here's some handy formulas in this section, and you should take a minute to try to think through them, see if you can remember them, see if you can do them without actually doing anything like a formal product rule, chain rule, quotient rule, u substitution thing, because you won't want to be doing that in the middle of doing an integration by parts. So hopefully you're remembering the a here gets multiplied on the outside as well. So it's a times cosine at. That comes from the chain rule. This is a times negative sine at, and this is a times e to the at. And then how about the integrals here? What's the integral of sine at? If you did a u substitution, u equals at, then you end up dividing both sides by a, du equals a dt, divide both sides by a. So you get 1 over a times negative cosine at. Here we get 1 over a times sine at, and here we get 1 over a e to the at plus c, but we're not going to be worrying about the plus c's in the middle of integration by parts. All right, so those are some formulas that you'll need to have right at your fingertips at the front of your brain as we're working on all this stuff. In this section, it's important to check your answers by taking the derivative by hand, because that helps you practice the same skills, like these kind of skills that we're doing in reverse to do integration. And it's also a good idea to plot the original function, the antiderivative you got by hand, and then have Desmos compute the antiderivative of that. It's another good way to check. All right, so let's work on something like this, but a little simpler, just to get us started. Let's do integral of x e to the x dx. You might think u substitution. I know I said above it doesn't work here, but let's just think about what would happen. What might you try? U equals x. That basically never pays off in u substitution. You're just changing the name of the variable without actually changing the integral. So that doesn't help. Well, what else is there in the integral? E to the x. Then du equals e to the x dx. You end up getting integral of log u, because the only thing left is the x. And how does x relate to u? X is the log of u. Do we know how to integrate log? Not yet, but we'll learn it later in this chapter. So the only two reasonable ideas for u substitution don't pay out. Maybe we are reduced to guessing and checking. It's an interesting way to learn things, right? So we know the integral of e to the x by itself is just e to the x. Maybe the same thing works for this integral. So maybe the integral is equal to just x e to the x. Well, with any good guess, any guess at all, what should you do? Maybe check it. So let's check it. So what's x e to the x derivative if that derivative is equal to the original function? So I'm taking this guess here and saying let's take its derivative. So go ahead and take the derivative of that and see if you get the original integrand there. What method did you just use to take the derivative of that? The product rule. So it's x times e to the x prime plus x prime e to the x. Now, when you learned the product rule, like when I learned the product rule, you probably did the first thing prime times the second thing plus the first thing times the second thing prime. And that's fine. Here it happens to work out just a little easier to do it this way. I'm not saying one is right or wrong. They're both right. So did we get what we want here? This is x times e to the x plus 1 times e to the x. Is that what we started with up here? Is that equal to this? Nope. Well, was it almost equal to that whole thing? Well, yeah, we wanted that, so we can say officially, yay, here, we got what we wanted, but then this other part we did not want. So can we modify our guess to either keep us from getting that part that we don't want and just leave this part, or maybe we end up getting that, but then something else happens and that part disappears. So let's think about how you could modify the guess. We had x e to the x. We want something. It'd be nice if we had a guess that didn't need the product rule, so we didn't have this other term, but that doesn't end up working. What if we had something later, so we'd still get this and then get something later to cancel this part? So we could say, how about x e to the x, that's what we started with, minus e to the x. So go ahead and check that by taking the derivative. So that thing prime is x e to the x prime, just like before, plus x prime e to the x. So that's the product rule, and then minus e to the x prime, just that last part there. So let's say that's all from the product rule. And what do we get? X e to the x plus 1 e to the x minus, that's just e to the x. And these things end up canceling. And we get exactly what we wanted to get, what we first started with up here. So in general, the idea of guess, check, and adapt the guess is a good idea. Maybe we got a little lucky here with an easy problem. Maybe it would be nicer to have a formal method to do all this, and that's what we'll do in the next video.